Okay, thank you very much for introduction. And also, I really appreciate this opportunity to talk about our recent studies. Thank you very much. Today, I'm going to talk about the origin of first radio burst implied from the cosmic stellar mass density evolution. So I am Tetsuya Hashimoto from National Johnson University in Taiwan. And then if you can see my cursor, these people are collaborators in the papers that I'm going to show today. Okay, so let me get started. So this is the outline of my talk today. So let me start with introduction. So we already had a great introduction from the Professor Kumar and also other participants. Therefore, maybe I can speak many parts of this one. And then let me focus on the FRB population analysis, which is based on our recent two papers. After that, I will present our new papers about testing general relativity using fast radio burst. So based on these two papers. And in the remaining time, let me a little bit talk about a new telescope plan in Taiwan dedicated to the detection of nearby FRBs. So actually, Lin is going to submit this paper soon. So let me start. So, okay, this is just an introduction. So as you know, two game changers have arrived, which are CHIME and FAST radio telescope. CHIME is, Canadian radio telescope, which is currently discovering a lot of FRBs. And also FAST is the largest telescope, largest single dish radio telescope in the world in China, which is also discovering a lot of new FRBs, mainly from the repeating FRB sources. So here I show the number of FRBs detected per year as a function of year here. So as you know, actually before 2021, actually the number of detection of FRBs were kind of several tens, say more or less it's 20 number. This number was actually small before 2021. But after these two game changers, actually number of detection of FRBs significantly increased. So CHIME is just released more than 500 FRBs last year, and then CHIME will keep detecting about 1,000 FRBs every year. And FAST is also keep detecting more than 1,000 FRBs from mainly from the repeating FRB sources. So this 1,000 FRBs per year is much, much larger than the before. This is about 2 orders of magnitude more than before. Therefore, this sample is really revolutionary data. So it is time to conduct precise science using such revolutionary FRB data now. So here I select the key sciences to be addressed by future FRBs. I selected the dark energy here and missing volume problem, testing general relativity, and cosmic reionization history, and dark matter. So maybe there may be more than this. But anyway, so all of these things are key sciences in astronomy and astrophysics. If one of them can be resolved by using future FRBs, there might be a chance to receive a Nobel Prize in Physics in this FRB community. So therefore, actually, this FRB science is getting more and more exciting recently. So here I'm just encouraging people here. So this may be the chance. There may be big chance here. However, before we can use these FRBs as a useful tool to investigate cosmology or key sciences listed here, so before we do this, we have to understand the origin of FRBs. So actually, we don't know, the problem is we don't know what FRB is here. Therefore, revealing the origin of FRB is getting central in astronomy and astrophysics. So therefore, let me talk about this origin of FRBs first in my talk today. So from my point of view, the actually problem is that actually previous research tried to localize FRB positions in the sky to try to directly identify the FRB progenitors. So actually, I would say this is the most reliable way to identify FRB progenitors or FRB origins, because you can directly confirm what are there at the location of FRBs. So this is really powerful, but it's technically difficult. Actually, there's only one successful case which confirmed the origin of FRBs, which is actually confirmed to be the galactic magnetar. So other than this one successful case, actually there is no other direct confirmation of FRB progenitors yet. So in this sense, in terms of statistics, I would say this way is most reliable, but it didn't work very much in the previous studies. Therefore, in our paper, we actually changed our point of view to try to focus on the history of FRBs using 10 times more samples than before from CHIME FRBs. So what does this mean, history of FRBs? So let me explain these things in the next slides. So here I selected possible candidates, possible candidates of FRB progenitors, which include white dwarfs, old neutron stars, old stellar mass black holes, and magnetars, young pulsars. This is actually active supermassive black hole and supernova remnants. Maybe more than that. The problem is there are so many FRB progenitors here, then we don't know which is the case for the majority of FRBs, except for this magnetar case of galactic FRBs. So this is a problem. But let me propose that actually we can divide these possible FRB progenitors into two different types here. One is old object. They have very long time scale, say long lifetimes, which is comparable to the giga-year time scale. And the number density of such old objects, for example, white dwarf, old neutron star, old stellar mass black holes, number density of these progenitors should be proportional to the cosmic stellar mass density evolution, because stellar mass in the universe is basically dominated by old objects. Therefore, if you have more stellar mass, and then you should have more these progenitors in terms of number. And then another category is young objects here. Their lifetime is much, much shorter, which is mega-year timescale or even shorter. And then number density of young object is supposed to be proportional to or related to the star forming activity in the universe, because these progenitors are basically remnants of star forming activity in the universe. Therefore, if we have more star formation, then you have more progenitors in this category. And the point here is that actually this cosmic stellar mass density evolutions and cosmic star formation rate density evolution, these two things are already measured from galaxy observations, which are well known. And here I show the cosmic density evolution as a function of redshift or as a function of look back time here. And then, as I said, all the objects which their number density should be proportional to the cosmic stellar mass density evolution. This stellar mass density evolution is already measured from galaxy observations, which are shown by yellow line here. And the young object, number density of young object should be actually increased toward a higher redshift. So this increasing trend and decreasing trend, these two trends are really different. Therefore, by measuring the number density of FRBs, actually it can be a strong tool to constrain the possible origin of FRBs. So this is a basic idea in this paper. By the way, if you have any question, please don't hesitate to stop me. I think anytime you can stop me and then please ask a question. And then let me show one clear example, which is about another astrophysical source, which is actually long gamma ray bursts. So long gamma ray bursts are known to be associated with star forming activity in the universe. So if you plot the number density of long gamma ray burst as a function of redshift here, which is shown by a black cross here. And as you can see, there is a clear increasing trend toward higher redshift. So this increasing trend of number density of long gamma ray burst is kind of synchronized with increasing trend of cosmic star formation rate density evolution. which is shown by the red line here. So this observation result is kind of strong evidence that long gamma ray burst is related to the star forming activity in the universe. So actually, we already know that this progenitor of long gamma ray burst is explosion of massive stars, which is, yes, indeed, directly related to the star forming activity in the universe. So this result all makes sense. So my question here is, now how about number density evolution of FRBs? So we really want to plot the FRB version of this figure to try to constrain the possible origin of FRBs. So, and then actually, let me show the previous my paper. Actually, 2 years ago, actually I showed number density evolution of non-repeating FRBs, which are collected from Parkes radio telescope. And the number density, derived number density is shown by red stars here as a function of redshift. This is 2 years ago, based on all the FRBs. At that time, yes, we found that actually number density evolution is kind of constant over the past 10 giga year. So this almost a constant trend of non-repeating FRB number density is actually quantitatively consistent with cosmic stellar mass density evolution, which is shown by yellow here. And then even though, yes, we actually show that this is quantitatively closer to cosmic stellar mass density evolution, but there might be a question here. For example, this data point is okay, but for example, for data point at a higher redshift, actually uncertainty here is huge, and this error bar is almost getting attached to this cosmic star formation rate density. So therefore, actually, and also number of sample is small. Therefore, it shows quantitatively closer to cosmic stellar mass density evolution, but we didn't have a really conclusive answer here. And I actually presented this result 1 year ago. One year ago, last year. So actually, YITP had actually FRE workshop, and I presented this result. And I'm really happy to update this result today. And then now, you know, we have better sample here. As I mentioned, you know, CHIME just released more than 500 non-repeating FRBs last year. Therefore, we can use this much better sample to do constrain the number density evolution of non-repeating FRBs here. So again, let me show the number density evolution for two cases, cosmic star formation rate scenario and cosmic stellar mass density scenario here. This is shown up to redshift around 4.5 here. And then next, I will show our results derived from CHIME FRBs. So as you can see, the number density evolution of non-repeating FRBs from CHIME FRBs are shown by red stars here. And then we found that the number density clearly decreased toward higher redshift. This decreasing trend is consistent with decreasing trend of cosmic stellar mass density evolution if we use a 1% significance threshold. And also this decreasing trend is really different from increasing trend of cosmic star formation rate density scenario. In this sense, we conclude that this cosmic star formation rate density scenario can be ruled out with more than 99% confidence level. Therefore, actually, this is our conclusion using CHIME repeating FRBs. So this may indicate that non-repeating FRBs likely originate from all the populations. For example, white dwarfs or all the neutron stars or all the black holes, all the stellar mass black holes. And then actually, this is not only the FRB population analysis, but also there are other researchers that focused on FRB population analysis here. So let me briefly summarize related papers here. And then actually this table, the purpose of this paper is to emphasize the good point of our paper. Therefore, some point may be a little bit biased, but let me try to summarize. Okay. So basically, I want to emphasize the good point of my paper here. So from my point of view, there are several important factors in this FRB population analysis. One is here. So whether or not the analysis is free from the redshift evolution assumption. So because we want to understand the number density evolution against redshift, therefore, basically, we don't really want to have prior assumption of any functional shape of this redshift evolution. So in this sense, actually, yes, our analysis is free from the redshift evolution assumption here because we use the so-called Bmax method, which will allow us to directly measure the number density as it is. So we don't really assume any functional shape of redshift evolution here. So that means actually any functional shape can be reproduced by using our method. Therefore, automatically our analysis can also test all the population scenario. Then we use a beta sample, which is from CHIME. And the CHIME sample is really homogeneous. And then we conclude all the population here. So let me go one by one. So recently, Zhang and Zhang et al. 2022 also performed a similar analysis based on the same CHIME sample, but they constructed the FRB population models first. Then they feed the models to the observed data of CHIME FRBs. And then because they need to construct a model, therefore they need to assume some functional shape of redshift evolution part. Therefore, this is not free from redshift evolution assumption, but they tested both all the population and the young population to both. And then to conclude, all the population scenario is actually better explained the observed property of CHIME FRBs. And then before that, actually, James et al. 2022 also performed similar analysis, but based on different sample, which combined ASCAP and PARCS, two different samples. And then actually in their analysis, they didn't include all the population scenario in their model. Therefore, automatically their conclusion support young population here. And then AUKUS et al. 2021 actually tested both young and no evolution population of FRB number density. Then they conclude that both can explain using all this ASCAP and PARCS sample. And Zhang et al. 2021, actually they also again did a similar analysis, assuming both old and young populations based on the probably almost the same sample, combining ASCAP and PARCS to conclude both population can explain both. And then this paper is what I mentioned before, 2 years ago. So anyway, so for the two nearest papers based on new CHIME data, both of the two papers indicate that all the population will be more like the case for CHIME FRBs. So therefore, let me conclude my this part. So using 10 times more samples than before, actually,
can I ask?
Sure.
So the non-repeater in your old paper remains a non-repeater in your new paper?
If I remember, non-repeater, actually, all the paper, I use the PARCS sample.
Right.
Therefore, I don't think, actually, I don't think non-repeating will be changed to repeater.
Okay.
But anyway, this time I use a different sample here, CHIME. So.
And one more question. So
sure.
If the FRBs are distant, they tends to dimmer, fainter.
Yes.
And it may bring some bias. Do you consider such a bias?
Actually, so we already know that how the apparent brightness change as a function of redshift. Therefore, actually, we already take it into account in our analysis.
Thank you.
Thank you very much, Yoko-san, for question. Okay. So basically, our conclusion is, so non-repeating FRBs likely originate from old objects. For example, white dwarf or old neutron stars or old stellar mass black holes. But I think I have to leave two cautions here. One is actually we excluded some FRBs with high scattering timescale because it's very difficult to detect FRBs with high scattering timescale using CHIME. Therefore, this completeness correction for such population becomes very highly uncertain. Therefore, I actually try to exclude such population from our analysis. And also, this is actually kind of universal problem. So we also try to exclude faint FRB populations because they also have high uncertainty on the completeness correction here. Therefore, actually we excluded FRBs with high scattering and low fluencies here because these populations CHIME cannot correctly detect and CHIME cannot correctly correct for the completeness correction. And these populations are missed here in our analysis. Therefore, if there are significant number of such populations, probably it may affect future results. Therefore, I think in terms of observations, it's very important to explore new parameter space with high scattering and low fluence here. That might be one of the future directions of FRB observations. So
can I ask?
Sure.
So I'm pretty sure here in your analysis, you're for the redshift, you're using the dispersion measures.
Exactly.
But we know that the dispersion measure from the host can be large in certain cases. There's at least one case where it's like 900. So you must have assumed the host dispersion measure distribution. What was it? Did you assume something like a log normal, like what McCart are doing, or what did you assume?
Thank you very much for question. That's a very important question. So actually in this analysis, I actually assumed the typical contribution from host galaxy, which is say in this figure, I assumed 50 parsec centimeter cubic. So I just assumed a single value. And then we also tested a different value of these assumptions. And then we confirmed that this conclusion actually doesn't change. But your point is really important. And then just for backup, so this is actually limited sample, but actually using our assumption on the rate of shift derivation, actually we can compare the spectroscopic rate of shift and rate of shift derived from dispersion measure. And then so using our method, actually we can compare these two. And then one by one relation is here. And then basically within the uncertainty, our assumption is actually consistently reproduce the spectroscopic rate of shift. But of course, you know, the number of samples is small here. But as far as we checked, actually we don't see really significant problem regarding the host galaxy component assumption. And then maybe one more thing is probably Inoue-san's point is very important because some host galaxies show very high dispersion measure contribution. But as far as I know, the number fraction of that kind of host galaxy is still small. Say currently we have 20 host galaxies identified. And out of 20, there's one case which shows very high dispersion measure. Therefore, actually that is kind of 5%. Then because we are doing statistical analysis here, therefore that 5% population may probably less affect our conclusion here.
Okay, but ideally, I guess in the future, you'd like to really test this with actual well, limiting it to really spectroscopic redshifts, I guess.
Exactly. That's always better. Yes.
Okay, thank you.
Thank you very much.
Sorry, what is a transparent point?
Sorry, this is actually, I wanted to check whether or not, because this is a Vmax method, therefore I need to define redshift beams for my analysis. And I wanted to check if this different redshift beam can affect our result or not. Actually, we can arbitrarily decide this redshift beam in my analysis. So then if we adopt the different redshift beams here, actually I see the same conclusion here, basically. So yes. Okay. Is there any other questions? So if no, I think I don't have time. So, okay, if no more questions, let me move on to the next topic. So in my talk, let me discuss our recent paper, which is about testing general relativity. I believe this is kind of interesting. So here I really simplified the history of dynamics here. So this is too much simplified, but please allow me to explain. So it's too much simplified, sorry. But the point is, so Newtonian mechanics was proposed by Isaac Newton, right? This is great. The point is, so after that, the Michelson-Morley experiment revealed that the speed of light is always a constant in the vacuum. So this experimental result cannot be explained by Newtonian mechanics. And at this point actually initiated the idea of general relativity proposed by Albert Einstein. And then a point is there are so many physicists who are trying to find new theory beyond general relativity. So therefore, it is very good time to come back to the original accurate measurement of speed of light again, to try to find something beyond general relativity. So if we can find something beyond GR, it is a great discovery in the century. And then my talk is about FRBs. So I would say FRBs is kind of ideal laboratory to test speed of light. So let me talk about this one. So in GR, general relativity, actually there is kind of assumption, which is so-called Einstein's weak equivalence principle. Let me say WEP. So WEP is a statement that the speed of light is always the same for different frequencies, nu1 and nu2, under the same gravitational potential. So for example, there is a source which is emitting radio signal. Say in this case, this is a FRB source, which emits radio emission at different frequencies at nu1 and nu2. And then this radio emission propagates all the way to the Earth. And then this emission goes through under the gravitational potential. In this case, GR actually assumes C1, speed of light of photon 1, is exactly same as C2, speed of photon 2 at different frequencies. So actually this makes sense, right? So speed of light is always the same for the different frequencies. But this is kind of fundamental assumption made in general relativity. Therefore, I would say it is always important to test these fundamental assumptions. So if there is violation, if C1 is slightly different from C2, then we may expect a time lag between photon 1 and photon 2 because speed of light is different. Therefore, actually this FRB is an ideal laboratory to test this WEP violation. Because FRB travels the cosmological distances. This is a long distance. And eventually, when FRB arrives at the Earth, we can measure the very short time scale of arrival time. Therefore, this FRB is really sensitive to accurately measure the speed of light. And this is one example of FRB detection, which is observed frequency in y-axis as a function of observed time. So, there's a detection of FRB here. And then, yes, we do detect time lag between different frequencies, but this is not because of WEP violation. So we already know that this is actually explained by plasma effect dispersion measure, because this tilt line is actually exactly following inverse square, new square law. Therefore, observationally, actually this time lag between different frequencies can be explained by using only this dispersion measure. We don't see any significant deviation from new inverse square law. So this means if there is a WEP violation, so that kind of signal has to be the smaller than the observational uncertainty. So otherwise, if it's beyond the observational uncertainty, we should be able to see the significant deviation from the inverse new square law. But actually, observationally, we don't see that, basically. That means if WEP is violated, this violation has to be smaller than the observational uncertainty. This can place the upper limit on the WEP violation. So this part is a new idea in our paper this time. So, okay, no time. So when people try to constrain this WEP violation, they use a parameter here, say delta gamma, which is defined as gamma 2 minus gamma 1. This delta gamma, gamma 2 minus gamma 1 should be exactly 0 when GR is the case. Speed of light is exactly the same for different frequencies. But what we want to do is we want to put an upper limit on this delta gamma parameter. And then according to, for example, different literature, Minarozzi 2019, actually this delta gamma can be parameterized as like this. So we use this delta T obs is, sorry, this is observed time lag. This is really observed time lag between different frequencies. And then you want to remove the already known physics here because we already know this physics, right? Yeah, you subtract this component, time lag due to the dispersion measure. And this upper limit actually also depends on distance to the source. Because HRB is coming from distant universe. Therefore, we have large number here. Therefore, we got very small number for this term. And also this part, time scale is very short. Therefore, we also get a very small number here, meaning that we get a stronger constraint because this is the upper limit. The new point in this paper is we use observational uncertainty on the arrival time, which can be converted from the dispersion measure uncertainty. But anyway, we can, yes. Okay, maybe I can continue. So we can use observational uncertainty here. This is our new idea. And then this upper limit on delta gamma is shown in y-axis here in the log scale as a function of observed frequency. And then actually there are many other constraints from other literature which are shown by black markers. And then our calculation are shown by red dots here. So, because we can calculate the arrival time uncertainty for individual FRB, therefore, actually one dot in this figure corresponds to one FRB. And then some FRB show stronger constraint, but some FRB show the weak constraint. So anyway, because this is upper limit, therefore smaller is better constraint. And if you focus on the best constraint from our data, this is actually more than 3 order of magnitude better than previous works. So that means using our method, we achieve the most accurate test about WEP violation than ever. So this indicates the feasibility of FRBs in this subject. And then, as you may notice, actually we used FRB cat. This is FRB catalog, but this is old. Therefore, actually we can improve using this analysis using a new FRB catalog from China. And then, as soon as we publish this paper, our one student in Taiwan, Kaustubasem, is from India. As soon as this paper was published, he applied our method to the new Chime catalog. And then our previous data point is shown by blue here. And then when we use the Chime new sample, actually which are shown by red dots here. And then smaller is better again. And then he achieved even one order of magnitude stronger constraint on this WEP violation using chime FRBs. So therefore, currently he is kind of record holder in this subject. His constraint upper limit is most accurate test on the WEP violation regarding the speed of light.
Well, I have a question, Hashimoto-san.
Hi, yes.
I think that for this one that you use Shapiro time delay, right?
Yes, exactly.
And as you know, that things are, you know, it's difficult to estimate the absolute value, right? You need to,
Right.
I think that that's always kind of, this is under debate, and then not so easy to evaluate the large scale, you know,
Right.
unless you know the exact value of the large scale structure contribution, then it's very difficult to believe the absolute value, right?
Yes, that's a very good point. So yes,
I think that you probably assume something which are subject to the lot of uncertainties, right? So the question is that the systematics can be larger than what you claim, right?
Yes. Yeah, exactly. So you are right. Actually, this is still in the debate as far as I know. And actually, I used an analytical formula from other literature, but that literature is still under discussion. So my point here is, so actually that part, how we can describe the contribution from a large scale structure part, basically related to calculation this term.
Yeah.
And then FRB, okay, other than this part, actually FRB always gives a better constraint regarding this time scale things. Yes. Therefore, that means, so anyway, when we calculate this delta gamma parameter, anyway, we need to unify how to calculate this upper limit, right, for different samples. And then when we try to unify these samples, actually we use all the same equation, basically. So this equation is not really confirmed well, but we can assume this equation or another equation, or anyway, we have to unify this equation. And then once we unify equation, so anyway, FRB has always advantage regarding this short time scale over other astrophysical sources. Therefore, whenever we assume any function, any cases under discussion, actually we always achieve better constraint than before. So therefore, you are right. So this absolute number of delta gamma depends on so which equation we assume. But this relative, how to say, relative improvement compared with previous paper is always the same.
But in that case, as some people discuss, it's probably better to use the statistical properties, right? And maybe because once you have, I'm not sure how many samples you use, but once you have probably 100 or even more, and then basically you can actually cancel the contributions on, then in principle that you can actually use the statistical properties to place potential constraints on the gamma.
Right. I think that's a very good point. Actually, are
you kind of working on this kind of analysis? And I think some people
I really willing to work on that kind of subjects. Say, yes, statistically we can constrain. And also another way, maybe we can stack all the data and then try to get high signal to noise ratio. And then we try to calculate maybe even better constraint using stacked analysis. But anyway, I think this is just for individual constraints, but I think there is a room to do something better using statistical analysis. So yes, you are right. So I'm willing to do that. Is that answer?
Yes. Thank you.
Okay.
Thank you very much.
Thank you very much. That's a really good point. But I didn't really think that. Thank you very much. So, and then anyway, I believe that this improvement should be the same always, regardless of the assumption here. Therefore, due to this impact, Actually, these two papers were featured by Internet News here. And then let me conclude this part. So, okay, I don't have time. So we propose a new method to constrain the WEP violation using fast radio burst. And then we achieve the most accurate test than ever. And then even when use older catalog, the achievement is 3 orders of magnitude better. And then when we use a new chime catalog, we can achieve even 1 order of magnitude better constraint on WEP violation. Okay, this is our conclusion on this part. And then if no more question, let me move on the final part of my talk. So this is really not my own research, but this is really kind of advertisement. So therefore, please allow me. So actually, we want to build a new telescope dedicated to the FRB detection in Taiwan. The name is BURST. So this is just advertisement. So actually in Taiwan, we actually started to try to think about the bottlenecks. So what are the bottlenecks regarding understanding the FRB origins? Then probably there will be 3 important factors here. One is lack of localization capability. So, you know, localization is always important because the SPEC-Z or host galaxy identification or direct identification of progenitors, all of these things come from the localization. Therefore, this is our most important factor, I think. But unfortunately, the current most powerful survey FRB telescope, CHIME, doesn't have this localization capability for now. They will have later in future. But anyway, this is very important to have for future telescope. And then again, the current CHIME telescope has small, this is still small field of view. That means the cadence of CHIME observation is really low. For example, for each source, but this depends on the declination of the source, but say on average, typically CHIME has only 5 to 10 minutes exposure time for each astrophysical source per day. So this time window is less than 1% of the during the day time, right? 1 day. So this means we have a lot of chance to miss possible FRB emission because the time window of CHIME is really limited. There must be a lot of missing population of FRBs here. To compensate this one, maybe one way is to use follow-up observations, but using follow-up telescopes, then it is always expensive. We cannot monitor for so long time using radio telescopes. So therefore, we want to really expand this field of view to achieve high cadence. High cadence means long continuous monitoring observations. This is really important to compensate this missing population of FRBs. And then the third factor would be mismatched distance. What does this mean? So actually some theoretical models of FRB progenitors predict association between FRBs and GW gravitational waves, neutrinos, and multi-wavelength counterparts. And then current facilities to conduct GW, neutrino, and high time resolution observations are all dedicated to the nearby universe. They cannot reach distant universe. And then what we are finding from CHIME is kind of distant FRBs. Say CHIME sample include redshift 0.5 or redshift 1 or so. So these are actually too far to coordinate simultaneous observations using current facilities. So therefore, we really want to dedicate to the nearby universe. In terms of revealing the origin of FRBs, it's more important to conduct complete observations in the nearby universe so that we can maximize the chance to have simultaneous observations with different facilities, multi-messenger, multi-wavelength observations. So these 3 factors are probably bottleneck currently we are facing. Then Professor Willie Penn, he was in China before, then he just moved to Taiwan and then to launch this new project in Taiwan. This is Bustling Universe Radio Survey Telescope in Taiwan. We say BURST. And then burst is dedicated to detect local FRBs with accurate localizations and with very wide field of view. So burst will have initially 256 antenna, which is located in Taiwan. And also this will include 64 antenna in Hawaii. And then using these baselines, we can do the interferometric observations to achieve accurate localization of FRBs. Therefore, I am involving this project, and then we aim to make this burst telescope the world's best telescope to detect nearby FRBs. So this is a goal of this project. And then actually burst can localize immediately when FRB is detected with sub-arc second localization accuracy. And a field of view is burst is designed to have 25 times better than that of chime, which will significantly increase the cadence of observation. And a burst, actually burst cannot detect distant FRBs, but it's okay. This is dedicated to the nearby universe so that we can really maximize the chance to coordinate the merge messenger and merge wavelength counterpart search simultaneously. And then this is just, okay, introduction. Currently, there are several students who are working on this project. One is Simon Sisiho. He is going to predict number of FRBs to be detected with burst telescope. Especially, he also focused on number of gravitationally lensed FRBs in his paper. So, and also another student is Desmond. He is also trying to predict number of galactic FRB-like events. So because this is focusing on nearby universe, we should be able to detect galactic FRB-like events too. And then he's also trying to estimate number prediction of that event. Anyway, they are going to publish the papers, submit the paper soon. Therefore, please looking forward to their papers. Okay, so at the end of my talk, let me conclude. Actually, my conclusion is very simple. So as you know, actually this FRB science can include many key sciences in astronomy and astrophysics, say dark energy, missing volume problem, general relativity, cosmic reionization, dark matter. So all of these things are really exciting. So therefore, let's encourage this community in future. Okay, I stop here. Thank you very much.
Any questions, comments? I have some questions. So as for BUS, what's the timeline, and can you tell the exact field of view of BUS?
You mean this telescope?
Yes.
Okay. I think this is a little bit confidential, but I think it's okay. Yeah. Maybe within this conference, I think it should be okay. So this is so this is a field of view as a function of sensitivity, and then field of view is basically comparable to that of STEAR 2, but sensitivity is much better than this. So this is our plan. Actually, we have two stages here. Initial plan is here, and then later we try to increase the number of antennas to get better sensitivity. So its field of view is, in this diagram, it's 10,000 square degree.
Sorry, STAR 2 corresponds to the, which one? Okay, triangle. Okay,
STEAR 2 is here.
I see, so sensitivity is 10 to 4 times better than STAR 2.
Right.
Oh.
When will the project start?
Oh, sorry, maybe I shouldn't say details because this is, well, actually, this really already started this project. The component that we can immediately start. And then for main part of this antenna, actually we submitted a grant, and then we just finished the interview, and then we are waiting for the results. So as soon as the grant is approved, I think we can immediately start. But actually, we already started some components that we can immediately start.
Sounds impressive. Thank you. Inoue-san, please.
Yeah, I was also going to ask about the sensitivity, but you already showed it. One more thing. So can you just remind me? So I think Chime has this project of outriggers to increase the angular resolution. So this is even longer baseline than Chime outriggers, and so you can get the best angular resolution. Is that correct?
I believe so.
Mhm.
I believe so. But Chime still has better sensitivity. Therefore, in terms of this resolution, spatial resolution, and this cadence, these are still better after they construct outrigger.
I see. Okay. Thank you.
Thank you very much.
Yes, can I ask a question? The very interesting talk and very interesting work. I would like to ask you about the distribution of the FRBs that you have found its evolution with Redshift, where you use the Chime catalog, and is it corrected for various selection effects that Chime has got? That's my one question. And I think maybe you have said already that this has been corrected for Chime selection effects, but can you just clarify that, please, for me?
Yes, actually, yes. In the original Chime catalog paper, they presented a selection function depending on different parameters. These things are all taken into account in this analysis. And then, so they show, say, I think if I remember, 4 different selection functions, say for fluence, scattering, duration, and dispersion measure. So these, they independently measured this kind of completeness, say selection functions. And then we actually corrected for these selection functions for our sample. And then in this procedure, actually, we didn't want to include high uncertainty to correct for this selection function. Therefore, we actually removed some FRBs with very high scattering and with low fluencies because they have highly uncertain selection functions. So this part. So basically, in short, yes, the selection functions are included in this analysis.
Yeah, okay, great, thank you. How much of a difference will it make? You assume that the contribution to DM from the FRB host galaxy is some fixed value. I think you said about 50 parsec per cc. That is what you had taken. How much of a difference it will make to your distribution
Yes.
if in fact this contribution was also redshift dependent? I don't know if you have tried that, and I wonder if that would make much of a difference to your conclusion.
Thank you very much. I think that's a very good point. Actually, that is also one of the referees' requests about this paper.
Just to make sure I was not the referee.
Yeah. So we did it. So with different assumption on the host galaxy component. For example, in this analysis, we assumed a different number for host galaxy component. And then actually what I see is that this decreasing trend anyway doesn't change when we assume different value for DM host. So that's our conclusion.
One final, very brief final question.
Yes.
Did you try comparing what you found for this Chime, using the Chime burst with the sample of 19 burst for which we know the host galaxy. Therefore, we know, well, the redshift and the host galaxy is known. I know that it's a very small sample, but did you try kind of making, based on the 19 known FRBs with redshift, to find what the distribution is and see if that is consistent with this different technique, much larger sample.
I see. I understand your point. So maybe what if you check this number density distribution using already known spec-D sample?
Yes,
that's the question. So
that is the question.
I think I didn't do this one because one reason is this spec-D confirmed sample is kind of heterogeneous. Then it's very difficult to calculate survey volume. That means it's very difficult to calculate the number density of that kind of sample. So for example, there must be many, complicated observation bias there. I mean, when I try to use spec-D sample, because spec-D is provided from optical sample, right? And then radio observation is radio. And then actually, we already have two different things here. And if host galaxy is very faint, of course, we don't get spec-D sample, then in order to calculate the number density, we have to correct for all of these things. But that's, I believe, it's technically very difficult to correct for that effect, observation bias. And then therefore, I always use a homogeneous sample, which we already know the sensitivity, we already know the survey volume, we already know the survey time, we already know the selection functions. So only when we can achieve these parameters, then we can correctly calculate the number density of FRBs. But in that sense, using spec-D sample, to me, it sounds very difficult to correctly calculate the number density.
Yeah, no, thank you. I think your answer makes very good sense. I appreciate it. Thank you.
Okay, thank you very much. But I think that's future. If we can conduct, yes, complete survey of spectroscopic observations, then maybe I think it's maybe possible.
Yes, indeed. Thank you again.
Thank you very much.
Please. Maybe you.
May I ask a question?
Sure.
Please.
Oh, hi, Tetsuya. That's
Hi.
a wonderful talk. So I have a question, actually comment / question for the second part, which is the web part. Yeah, I know there are many papers on this subject, and myself was also on one or two of those papers. The web, the
web. Oh, sorry, the web.
Yeah. So yeah, because you make very important. It would be very important if you discover some theory beyond GR. But all these tests actually, after all, only goes to the other direction, because we have no way to say that web is violated. We can only say that it is not violated to a certain extent. It becomes more and more precise towards GR. Of course, we can use different methods and write more papers and just say, okay, GR is great to what precision. But in general, what's your opinion on this very broad general direction of this field?
I really agree with your comment, actually. One difficulty is, say, what we can do is basically only put upper limits, and then we can make it more accurate and more accurate. But in order to reveal the violation, we have to find something beyond or deviation from the dispersion measure relation. So even when we find something deviation from that, it might be actually because of the intrinsic property of FRBs.
Yeah, astrophysical things.
That's a good point. Yes. Then I'm not sure, but maybe one way is try to find something universal. For example, this physics should be universal, right? So all of the FRB has to be affected by the same universal physics. But of course, there must be intrinsic variation, I mean, in terms of FRB properties. But when you try to, if it is possible to try to extract something common in this time round, then it might be a hint to discuss possible violation. So that's might be one answer. But it might be difficult. Probably we need to have many samples here, and then we need to find something common in the older sample. If we find something, then it might be violation. That's my understanding.
All right, thanks.
Anything else? If not, let's thank our speaker again. Thank you very much.
Thank you very much.